Hi, welcome back to Risk Management. Today's topic is entitled Financial Risk Part 4, Chaos or Causation. All along we've been talking about fractals and we've talked about how financial markets appear to have a complexity to them that's not modeled through simple cause and effect relationships. The question is, how do we know, if we think all the way back to all those lectures that we had about causation, that any given set of relationships are in fact causal? How do we actually know that we're not underestimating or misestimating it, and that it's in fact a fractal relationship? Well, that's some of the discussion of today's lecture. It's a complicated subject, but we'll try to boil it down to its essence, and then move on to some of the factors that are deterministic, that are perhaps overwhelming the system in financial risk and creating significant problems for us in a future lecture. So first we have to return remembering what a fractal is. It's a geometric pattern that is repeated at ever smaller scales to produce irregular shapes and surfaces, roughness, that cannot be represented by classical geometry or by simple cause and effect relationships if we're looking at something like financial volatility. A fractal contains infinite length in a finite area. Effects occur unpredictably inside the fractal, but not outside the fractal. That is, it has boundaries and has limits, but within those limits, it's hard to predict what's going to occur. For example, if you look at the irregular shape of a mountain and then look closer at the smaller parts of a mountain, you'll find some of the basic shapes of the whole mountain reflected again in the little parts of it. There's also going to be some randomness built in there, but you will see those triangulations, as we saw in the last lecture, in the small parts of the mountain, just as you see in the overall mountain. Here are some more pictures just to show you how nature in so many different ways incorporates fractals in order of a sort of chaotic nature into it. There is a pattern, there is some sort of sense of order, but it's chaotic. It's not the sort of smooth, linear type of causation relationships we saw where A causes B in all of those lectures that we did on causation. Here's another example of trees and their fractal patterns. Or you can see it in a broccoli stalk, or in a cauliflower head, or in lightning, or in the fern or a leaf, or in the lungs, or in a coastline. Here's Norway's coastline, and you can see the fractal patterns of it. Here's another picture of the Earth with fractal river tributaries laid out. Here's the Badlands in South Dakota, and you can see the fractal patterns of the erosion that's occurred there. Mandelbrot actually asked a question, which was, how long is the coastline of England? And if you start in the top left, he took a satellite photo of the coast of England, and then he zoomed in picture 2, upper right, on a portion of that coastline. The upper left quadrant in the first photo was zoomed down and created a photo in the second picture on the upper right. And then he zoomed in again on the upper left quadrant of that photo, and then he zoomed in again on the upper left quadrant of that photo. And so you've got this pattern where he goes around here, and as you zoom in and in and in, it's hard to tell what perspective or sense of dimension or scope you are actually looking at the coast of England. Number 1 could be the zoomed in photo, or number 4 could be the zoomed in photo. It's hard to tell in looking at this. So it's actually hard to estimate the actual length of the coastline of England because the complexity becomes so difficult the closer in you look at the photos, the more complexity there is. And notice that not all coastlines are like this. Some coastlines have fractal patterns to them, and others seem quite smooth, such as these 2 photos demonstrate the difference between them. And the reason actually that scientists think that one is occurring versus the other is because of the land's attempt to mitigate erosion. And so where there's larger wave activity or more sensitivity to erosion, the coastline will become more fractal in an effort to inhibit more coastal erosion, whereas where there's less such wave activity, the coastline can be more smooth and classically geometric in shape. So Mandelbrot said when he was talking about this that one of his points in inspirations in creating fractal geometry is he noticed that clouds are not spheres, mountains are not cones, coastlines are not circles, and bark is not smooth, nor does lightning travel in a straight line. And what we might add to that is, nor do prices behave in normal rational ways with a sort of mean reverting activity and sort of very smooth transitions in pricing. There's extreme volatility with spikes and recursions and so forth going on in pricing. And as a result, because of both the Noah and the Joseph effects that we spoke about in the last class, that prices tend to travel to the extremes and tend to stay there once they reach extremes, we know that we're not dealing with normal sort of relationships where, for example, a simple injection of additional money into the economy causes a very smooth change in how things are supposed to occur. This will have implications for us when we're thinking about monetary policy or fiscal policy and its effects on the economy, because when we look at prices on the exchanges, we see them to be more fractal in nature than we do smooth geometric patterns or normal distributions, Gaussian distributions. So how are fractals determined? I don't want to turn this into a math class where we're going into the actual details. What you need to know is there are actually just two things that set up a fractal. First is you have to know the initial conditions that you're dealing with. In what order are you placing a few dots or a few little triangles or something relative to each other? So you need to know the initial setup of your pattern. You then need to know a rule by which you're going to change your pattern. So for example, here is Cox snowflake. And here in box 1, we have a simple triangle. And what we're going to say is we're going to create an additional triangle that's halfway between the ends of each of the sides of the first triangle. So that's the rule. The first condition we have is condition 1, a simple triangle. And then we're going to create a rule. Wherever the triangle has a side, put a new triangle along that side midway between the two endpoints. And we do this over and over and over again as a rule, and then out of this emerges a pattern where infinite distance is created in a finite space. And this one in particular, on the bottom of the page, as you do this over and over and over, you create something called Cox snowflake. You can do this again with any number of different things. Here's Sierpinski's gasket and triangle, where you can take simple patterns. The initial pattern is a simple box with a hole in the middle, and then you create a pattern of additional holes in the middle, and eventually you can create this box shape out of it. And the same goes with the Sierpinski triangle. You could create a triangular shape with similar patterns out of it. This is done by man throughout the built world and the constructed world. Here's the Eiffel Tower, which has a fractal pattern to it. And then the Julia set, which is something that was mentioned in an earlier lecture, Mandelbrot himself created using computer programs, beautiful fractal patterns, where he set up some initial conditions. To make it simple, you'd put a triangle here or a little shape there, and then created a rule to operate on that initial condition, and out of that emerges some other deep pattern. And if you zoom in on any part of this pattern, you see that initial condition replicated again. For example, here that red swirl is replicated over and over at more and more narrow intervals as it goes along. You can actually build up things that look like nature doing this. So here's somebody with a little bit of dust in the top left that has a rule that they have the starting condition of this dust sort of laid out, and then they have a rule for multiplying itself. And so you can see the fractal pattern taking shape as you go along the top right row. And then again, as it grows and grows, it turns into a fern. And there's the shape where with a simple set of dust patterns and a simple set of rules, we can create something that mimics nature. You can do this even with the brain, where you take initial conditions and certain rules, and then you can create what looks like a good fractal prediction of what the brain would look like and all of its neural networks in the brain. So very impressive that using simple geometry and a simple set of mathematical rules, we can create extremely complex patterns in nature that are replicating nature. Is that how nature actually did it? Well, that's beyond us to know. We don't know nature's initial starting conditions or the rules that were incorporated into creating nature. What we can say is these pictures look an awful lot like what we find in nature, and we can do it very simply using relatively easy mathematics. One other thing to take into account here is something called the butterfly effect when we're dealing in fractals. This is the famous story of the butterfly flaps its wings in China, and the next thing you know, there's a hurricane off the coast of Florida. That very small changes, either in the initial starting conditions or in the rules that are applied to create additional rounds of iterations of the fractal can dramatically change the outcome that we get. So models that attempt to simulate chaotic conditions or fractal conditions are very sensitive to initial conditions and changes in the rules. You can create very dramatic outcomes that are not causal in nature at all. Who would think that a butterfly flapping its wings could cause a hurricane? And yet in the models we create, such scenarios can come out. It's probably why, for example, if you look at snowflakes, and you've heard the old saying that no two are alike, here's an example of a whole bunch of different pictures of little snowflakes, and indeed, look at how dramatically different these snowflakes are. That's probably because the nature of a fractal snowflake is such that it's very sensitive to the rules on how it's created. If we're doing a computer program building this, when and where the snowflakes fell, what were the starting conditions for that snowflake? For example, how much water was there in the air? What altitude did it start forming at? What was the temperature? Were there any external shocks to the snowflake? Did they bounce off of other snowflakes that would influence the conditions under which it formed? And did the rules by which the snowflake was changing itself change over time on the way the flake fell down? So you can notice that with all of these very sensitive considerations, it's very hard to make any sort of predictions in advance about what a given snowflake would look like. What we can say is we can replicate these types of snowflakes under computer conditions where we start with a certain set of conditions and we apply a simple rule. Doesn't mean we're going to be able to predict in reality what a given snowflake looks like. So why does this matter to us? Well, it's part of the concern we have whenever we're talking about causation is, are we actually dealing with conditions that are not causal, but rather fractal? And the problem with that about a fractal system is, number one, our initial conditions don't tell us the rules that are going to govern and create the fractal. Number two, the rules that we use to create the fractal don't tell us anything about the initial conditions that were there when the fractal started. And number three, without knowing the initial conditions, the rules alone will not predict for the fractal pattern. Number four, without the rules, the initial conditions will not predict for the fractal pattern. And finally, even if you have the fractal at the end of the day and you see the full picture, the fractal doesn't tell you the rules or the initial conditions you're dealing with. So we can never quite back out, if we don't know the initial conditions and the rules that are going to apply, what a given scenario is going to look like. In other words, we can't do something the way we do simple causation, where we say starting with A and a small change in it and knowing the rule of causation, the determinism that applies, we can predict outcome B, the effect. We can't do that with fractals. There's so much sensitivity to what the initial conditions are and the rules that it's impossible to back one out without the other. That doesn't mean that everything in nature is fractal. So here's two different waterfalls. The one on the left has sort of a fractal set of divides and patterns to it. The one on the right is relatively smooth, looks more like a causal type of relationship. The water falls and it hits the flow below. It's a very smooth, linear, deterministic type of pattern. And yet, why is it the case that one is fractal and the other is deterministic? We can see this also, for example, in a water wheel that goes around. A water wheel can either be fractal in its rotation, or it can be deterministic, causal in its rotation, depending on how the water is that drops onto the water wheel. If we pour water out at a huge rate out of this tube above the water wheel with a lot of flow and heavy force, we can predict very well in sort of a causal relationship how that water wheel is going to turn. And it's going to turn at a certain rate and speed relative to the fast flow coming out of that tube above the water wheel. But if you didn't pour water out of that water wheel and you sort of let it just drift back and forth a little bit based on the air currents, and then at certain intervals just allowed for a little drop of water to come out and touch the wheel, you could create fractal patterns where the wheel might roll around in a certain direction for a certain amount of time and then reverse and go back the other way and come back and go around again the other way. And so it's much more sensitive and much less linear in its relationship. In other words, it has sort of a nonlinear or fractal pattern to how the water wheel rotates one way or the other, how long it rotates in one direction versus going back in the other. The same idea can also apply in different types of martial arts. Boxing is a very linear type of martial art. We punch, somebody gets knocked out. It's a very clear, linear relationship, force applied, effect as someone falls over. Compare that with Aikido or Jiu-Jitsu, martial arts that are very much more about timing and touch and very soft, sophisticated use of power where just at the right moment, at just the right balance, and in just the right flex or direction, someone's entire force with very little effort can be redirected in a dramatic way. That's the distinction between a chaotic system where very small inputs can have huge effects on the outcome versus linear systems like boxing where very strong inputs have very clear outputs. So to summarize what we've been talking about here, chaos theory or fractals state that small changes can result in large differences. There is an underlying order all around us, says fractals, but those fractals are harder to predict than we could with a causation theory. Chaotic systems, including fractals, are deterministic, so they are still have outcomes just as does a causation have an outcome. But it means something is determining their behavior. The problem is, unlike causation, it's very hard to figure out what that something is, and what are the set of rules governing that behavior, and what are the set of initial conditions on which everything started operating. The rules don't tell you initial conditions, and the initial conditions don't tell you the rules. Chaotic systems are extremely sensitive to the initial conditions or subsequent shocks that come from outside the system. A very slight change in the starting point of your price series could have enormous differences in terms of how volatile those prices become. This usually makes the system unpredictable. It's very hard to predict, even using fractal methods, what exact prices are going to be. It also requires for a fractal system to have advanced knowledge of all rules governing the system. This itself also makes the system very unpredictable because one can only guess whether the rules that one is setting up are the ones that nature or the stock market or whatever are operating by. So, in summary, the best use of chaos theory or fractals appears to be to know when it is inappropriate to use causal knowledge to estimate the markets, not to actually predict something itself. So we can rule out causation and say we're now in the realm of fractals, and we can create patterns that look like what's going on, and we know not to use causation methods here, but it doesn't necessarily mean we can actually predict what's going on. So hopefully that gives us a little more insight into the distinction between causation, where clear linear relationships exist, and we can deterministically, repeatedly estimate a certain outcome given a certain input, and we say cigarette smoking causes lung cancer, and we don't expect that's going to change tomorrow, the next week, the next year, based on sensitive inputs to the system, such as whether a butterfly flaps its wings in China. On the other hand, for stock market prices, maybe the fact that the butterfly flapped its wings actually does make a difference for the markets. It's very hard to model such things, but what we do know is causation doesn't typically work to model such factors. Okay, we're done for today. In the next two classes, we're going to pick up with this and talk about two areas where financial policymakers have tried to force the markets to behave in certain ways, and I'm going to suggest that not only have they not decreased the risk by doing so, but they have increased the risk of the markets because markets are fractal, and by creating detrimental starting conditions for the market is going to be susceptible to more volatility over the coming years and not less. See you in the next class, and I look forward to hearing from you on the chat boards.